Thank you very much. And just a short comment. I mean, the presentations before were really focused on more a system level. This is more, let's say, focused on a component development project. So that's also the reason why we are in this task. So the funding agency, they mentioned it would be nice to be in this task. So it's a funded project from the Federal Ministry here of Economics here in Germany. And yes, me myself, I work now since 12 years at Fraunhofer IFAM. I have just really short slide. I will not go into detail about this. So Fraunhofer IFAM in Dresden, it's really focused on material development. So we have a lot of material scientists here, but me, myself, and we in our group, we are basically energy engineers. Let's say we are the connection between the material scientists and the application of the materials. And in this project, two groups are involved. So one for the material development and we about energy and thermal management. And because thermal storage is one of our important topics here, but I will not show anything about, so I will really focus on this project. So the motivation for this project in principle, I mean, I think you all know about this process heat, what is a large demand in the industry. But yes, the reason why we do this project is on, if you look on compressed air, which is really important in the industry, you can see, depending on the sector, yeah, the share of electricity which is used to produce compressed air could be quite an important number here, so that you can see. Yes, in some industries, it's more than 15% of the electricity which just is used for compressed air production. And in the end, compressed air to produce it is typically quite expensive due to you need electricity, and then the efficiency of the systems is typically limited also. And that's the reason how we got into this topic. So from the thermal storage topic, we work a lot with latent heat storage systems, so based on phase change materials. And there you typically have, let's say, the disadvantage that you have a volume change of your storage material from the phase change between liquid and solid state. But in our application, we make use of this volume change. So in the end, we will want to have a, let's say, bed PCM, which has a large volume change. So we use waste heat to melt the PCM, use the expansion to move a piston and to compress air. So that's the idea. And in the end, when the PCM is completely molten, you cool it again to get it solid, and then it decreases volume again, and then you can do it again. So it's like a cyclic process that you do here. Some important parts about this is, I mean, maybe it's easier to just look on this animation, so how it works. So during the heating process, you will have the PCM, which increases volume, and during the cooling process, you decrease the volume, and then you move the piston with this movement, and then you produce compressed air as a cyclic process. One really important part about this, where the material science really comes here into the system, because I mean, for most of the components, you can use components which are available on the market, but an important topic regarding the economic feasibility is that you really need short cycles, so that you have a really good heat transfer in the PCM itself. So there we use these really porous structures here to integrate the PCM inside and use it as a structure to increase the heat conductivity. And yes, so this is an example which we use for aluminum fiber structures. Yes, and in the end, you can include, let's say, a large amount of PCM inside. So up to 90% of it could be PCM, depending on how you design the material. But yes, that's a really important factor about this application, because otherwise it will not be economically feasible anyway. So we made estimations in the beginning about the concept, and there you have to have times at around 1 minute for the heating and cooling cycle. So it is realistic to get into this range, but it's really, let's say, yeah, you need a really optimized system. But then you can also have systems with all the components which are yet comparable to other options to produce compressed air. Yes, so that's about the system itself. So at the beginning, we did some kind of proof of concept just to see if our idea would work. So we built a small scale demonstrator just to measure the force which is created by the PCM. So here you have the porous fiber structure inside. You have a cylinder with a channel around to use some liquid to heat it. For this demonstrator, it was before this funding project for this proof of concept. We just did the heating process, so just to measure if we get a considerable force that we could use for something. And if you look on the force which is created by the PCM and look on the area that you have here, you can get really it would be really high pressures that you could create. So it's yes, that was our, let's say, proof that it makes sense to look deeper into this technology. And yes, that's about this. Then during the project at the beginning, I mean, we started with this, let's say, easy idea about using a cylinder, but also in the project, we look on other designs. So there is this, there are different design processes that you could use. So for example, this norm from VDI in Germany, where you start from the requirements, then define your functions in the system. So for example, for the heat transfer or transfer the force in the system, and then you can get to a lot of different, then for every function, you find different solutions, and then you can make combinations of these solutions, and then you get to, in the end, to a lot of different designs, what you could evaluate, which makes most sense to look more deeper in it. So it's some kind of organized brainstorming process how to design the system. And yes, that's really, let's say it's a really structured process to get to different solutions. And so that's what we did in the beginning, but I will really focus on the cylinder development. So additionally, let's say to have let's say estimations for different applications, we did a really quick assessment tool. So based on a Stefan calculation about the solidification time of a PCM, just to show, just to look on the impact factors on this heat transfer topic. And what you could see here, I mean, in the end, the goal is, like I mentioned, to have 1 minute or something for the solidification and the melting process all together. So the aim would be to be at around maximum 30 seconds. So depending on the conditions that you use, that's possible. I will not go into detail about this now, but just let's say that was the first step of it. And also it's, let's say, for future quick assessments, just to look how the system should look like. That's a nice tool. But in more detail, then it's necessary to also make numerical simulations. But for the numerical simulations, as you know, that's also important to have good input data, because, for example, if you look on different PCM, in this case, we used RT42 from RubyTerm. So we could use a waste heat from 50 to 60 degrees around to melt the PCM. And yes, as you can see, yes, there is quite a difference between some numbers in the data sheet and also the measured data that they show. There's already a quite large difference. And also, yeah, that's the fitted model that we use for our numerical simulations that I show on the next slides. But we also did additional measurements just to look if this data is reliable. And the next step was to have a simple 2D model, just to look on yes, the influence also on different factors like thickness of the PCM or the heat transfer coefficient, or also the material. So what kind of material you use for the porous structure or the porosity, just to look in which range you have to be. So for a cylinder, for example, you see you have to have really thin thickness. So 10 millimeter is some kind of maximum that you could have for a cylinder to be in this range of 30 seconds that you need for the solidification or the melting process. And But let's say to look more on the system operation, we also built an additional model in OpenModelica, where we also coupled this with a volume expansion and the pressurized air production, so that we have some kind of thermal model here and a compression model. And in the end, we will extend this also to combine different of these compressors in the end. So because I mean, if you look on one cylinder, the amount of compressed air that you could produce is quite limited. So you need several of these, for example, cylinders or some other designs that you need to get to a higher compressed air mass flows. So that's the one. And here are some examples from this model, just to also look on in more detail about how the system operates. So I mean, in the end, what I already told here, you can see a little bit the cyclic operation of the system. So you charge your pressurized air tank, yes, in different steps with this compressor, always during the heating process, and then you have the cooling process where nothing happens. Yes. And in the end, what we do what we are currently doing to build up a demonstrator really for the cyclic operation, because this proof of concept was just, as I mentioned, just for the heating process and to look for the forces which are created. And now we build up a system to really do this cyclic operation. So also mainly based on commercially available components, just to limit, let's say, the cost of the system. Also, we use PCM, which is available on the market. I mean, we have an industrial advisory board in the project where we also discuss about other development topics where the system could be optimized, and also with RubyTerm, for example, to use other PCM. But as I mentioned, typically for this purpose, we need a, let's say, bad PCM. So we need a high volume change. And also it would be good to have a low latent heat, because then it's also the phase change happens faster. So that's in the end, we want to show it up to a pressure of 10 bar, which is a typical pressure also in the industry that they use. And yes, especially the cyclic operation should be one goal here. So just to summarize it, in the end, we want to use the low temperature waste heat to produce compressed air, since we think, and also, I mean, the discussions with other people, that they are really interested in this topic, because it's an additional option just to make use of this low temperature waste heat at, for example, 50 degrees or something, not just for heat pumps. I mean, if you have no additional demand for heat from this heat pumps, you could also use it for compressed air. And there are, like I showed, there are a lot of companies that need compressed air during their processes. Yes, large part now is the technology development and the lab scale demonstration. But let's say the important step where we already are in discussions with future partners is about the demo. I mean, that's what we do in the project, also the demonstration of other designs. So I just showed the cylinder case, but we also build other designs that let's say are sometimes better from the heat transfer topic. And also the next step, really important one, is to build an industrial demonstrator to really look on the operation in the industry, how it could be integrated and everything. Yeah, also the coupled operation that I mentioned with OpenModelica would be quite interesting, because as you saw, it's like a stepwise compressed air production. Yes, and also the economical things. I mean, we did a really rough economical estimation in the beginning, but as you know, economical estimations are always, let's say, limited from they are always based on the input data that you use. Okay, that's all from my side. And thank you very much. And if you have any questions, yes, you're free to ask.